In today's Daily Dose of Math, we are being asked to draw the front, top, and side views of this three-dimensional object. We're given some of the measures, and we're given the total volume. But there is a measurement that we are not given, which is this one. I'm going to mark it with X. This X is the same as this. If you see this shape as being the front of the object, then we're looking at the depth to find X. Now, a student, given these measurements, could correctly draw the front of this object without having found X. But if you're trying to get a good mark on the question, that's not going to get you very many marks, because you also need to be able to draw the top and side views correctly, and you will not be able to do that unless you find X. So I'm not going to start drawing the front view yet. I'm going to find X first. Now, given a volume, we want to use a volume formula, but of course this object is not one where we have a volume formula. It's a composite. We have to break it down into familiar shapes. If I draw a dotted line across here, then I am breaking this down into an isosceles trapezoidal prism and a right prism. If X is equal to 2 meters, then this right prism would be a cube, but we don't know that, and we do not want to assume that. We do not want to guess how long X is. To use the formulas for a trapezoid, we need the big base, which we're given, that's the 6 meters. The small base we are also given, that's the 4 meters, but we also need the height. The height of the two-dimensional object, the trapezoid, is this height here. And the only way of getting that is to do a subtraction. So it's a step, but it's an easy one. We are taking the 5 meters, which is the total height of the object, and we're subtracting the 2 meters, which is the height of the right prism. And we're able to prove that the height of the trapezoid is 3 meters. This might seem obvious, and you might be tempted to just use 3 meters without writing this down, but you will lose marks if you do that. You have to show where you got the 3 meters. Now, the volume is the total volume for both of these, so I need 2 volume formulas that I'm going to add together. The quicker, easier one is the right prism, so I'll start with that. The volume of a right prism is equal to length, width, height. I know 2 of those, which are 2 and 2. And this one's missing, and I will just call that X. So I end up with 4X as an expression for the volume of this part. Now we're dealing with the trapezoidal prism. Now, a trapezoidal prism, we don't have a formula that works with the big base as the base for the three-dimensional trapezoidal prism. We need to, in our minds, be able to tilt it up on its side so that this isosceles trapezoid is on the bottom. And therefore, this X that we're looking for is the height of that trapezoidal prism. So the area will be the area of the base times the height. That's the height, our X. The area of the base of a trapezoid is going to be big B plus little b times the height of the trapezoid over 2. So it is confusing. We have 2 H's that mean 2 different things in this situation. Let's fill in the numbers so that we can see what we're doing a little bit better with this. The big B is the 6, the small b is the 4. The height is the 3 that we calculated earlier. And we still have this other height, the height of the three-dimensional object, which is 10 times 3, which is 30 divided by 2. I'm simplifying. That is 15. And we still have that H. But wait, that H is the same as the X. I'm going to call it X. So we have 15X and 4X, which must be added together. 19X is the total volume of these 2 shapes, and it has to be equal to 57. Oh, now all I have to do is divide by 19, cancel, x is equal to 3. It is 3 meters. And I proved that it's 3 meters, I didn't guess it. Now we have enough information to do all 3 of the views, the front, top, and side, and it's time to start talking about our graph paper. Now I drew this graph paper in purple on this chalkboard, and I didn't draw it perfectly, but it's close enough so that we can visualize we have some graph paper here. The trick is to realize I can't put graph paper that's the size it would be on your page on the chalkboard. It would be too small, you wouldn't be able to see it. So I had to draw this enlarged version of graph paper, but I'm pretending that each square on my chalkboard graph paper is actually 0.5 centimeters by 0.5 centimeters, which is the size of a standard graph paper that my students would use in an exam. It adds another level of difficulty to geometry. When you are already representing one size object on paper of another size using a scale, and yet while the teacher is explaining how to do it, the teacher is using yet a third size, the chalkboard size. It is a little bit tricky, but this is what we're doing. We're pretending this is regular graph paper. And now I have to give a scale for my drawing. I'm going to write 0.5 centimeters equals 1 meter. That's the scale I'm using, and I'm choosing a very simple scale. It means that every square, therefore, is 1 meter by 1 meter, and when you see the size of the side lengths that we have here, that's going to make it pretty easy to draw our object. So now I'm going to start drawing, and I'm going to start with that front view that I could have drawn right from the beginning before I calculated my x equals 3 meters. The front view is this one that I'm tracing with my chalk right now. That's what the front view of this object would be. The isosceles trapezoid with a square attached to it. I'm going to start with the 4 meters. I'm going to leave myself a bit of space on my graph paper, and I'm going to draw a white line on top of the purple, make it nice and thick so we can see it well, 4 squares long, which by my scale means 4 meters. So that's working. Then, below it, this is 3 meters, remember this height, so I have to go down 3 squares, and I'm drawing another line that's going to be 4 squares long. That's this part. Now I'm going to get my ruler, where is it? And I'm going to connect these 2 ends. And I've drawn this line. Down here, I have to go down by 2 meters, so I have to go down by 2 squares on the graph paper. And across by 2 squares. Up by 2 squares. And now I have to draw another slanted line. So I'll use my ruler so that I can do that a little bit more neatly. I have drawn my front view. I'll label it front, and I want to label it with any information that I know about this shape that was given to me in the problem. So things I had to calculate myself I don't have to label, but things that were given to me I need to label. So I'm going to say 5 meters here. I'm going to give the 6 meters. I'll give this 4 meters. Notice that I'm not writing 2 centimeters, the drawing measure. I'm drawing 4 meters, the real measure. Drawings are useful when they show the real measures. I also know that this is 2 meters. This was 2 meters. I don't have to write this one, and I don't have to write that either, because it wasn't given in the problem. I'm not writing the height, 3 meters, it was not given in the problem. I have enough information so that I can see this drawing and understand it, which is the whole point of a drawing. Now, let's do a side view. Now the side view is kind of tricky. One thing is, which side? Should we draw the view of this thing from the right side or from the left side? Well, the good news is it doesn't really matter, because a side view is going to look like a flat two-dimensional shape, much like this one does. And so you're not going to see this angle. So the side view is going to be starting with 2 meters, which is 2 squares. I'll do it here. That's down at the bottom. Oh, no, I'm wrong. I calculated the x is 3. It's not 2, it's 3 that I need. I'll do it here. I want to make sure I leave room for all 3 drawings. Okay, so the side view, I need my x. And I figured that out. I'm going to label it 3 meters. Then it's going to go up by 5. That's this. So I draw a line, 5 squares. Remember our scale. Every square is 1 meter. It's an easy scale to apply. And then the side view is just going to look like a rectangle, but it would be quite lazy to not show any detail in the middle, because you would notice this line. So I'm drawing that line, and that's here. I'm writing my label for my 5 meters. And the 3 meters, and that's all I need for the side view. The side view is actually quite simple. And when you think about this shape, it would look like this from either the left side or the right side. Now we have to, I'm going to label also side view, so I'll write that with it. And now we have to do the top view. So I'll start by just writing top. Now what's the top view going to look like? We have choices really, because where do we see the top from? Are we approaching from out here where the camera is, or are we approaching from behind? Basically it's flexible. But we have to make sure that the top view is accurately reflected. Now the top view, you're not going to see this block at the bottom at all. It won't be visible because it's behind from the top, it's behind this other thing. So we're seeing the top of this isosceles trapezoidal prism. It's going to be 6 meters, therefore 6 squares in length. So I'm going to do that. Just barely fits. And I'll label it right away. And it's going to be x meters across. Now the x is the 3 meters we calculated, so I just have to go up by 3. Really, we have a rectangle. So it was a simple rectangle from the side, and it's a fairly simple rectangle from the top as well. And I'm going to label the 3 meters. I'm nearly finished. All that's left is that these 2 lines would show if I were looking at this from the top. And they're 4 meters. This thing is 4 meters long, and the whole thing is 6 meters long. But because it's isosceles, the 4 meters is centered within the 6 meters. So that means basically I can see that I would have a line here and a line there. And that is now a correct top view. If I want, I can also label 4 meters. I think this is a complete answer now. So what is it that would make this difficult if a student were doing it on one of the exams that I teach? I teach a course called Math 3053, which could have a question like this. What's different is when I make a video or a practice question for students, I tend to keep my situation as simple as possible. I want the student to be able to focus on, can they do the math to be able to produce what they're being asked for, and not to let them be confused by a big long paragraph. And a real exam question might have quite a big paragraph that puts this into a scenario. So let's create one, okay? And we'll talk about the idea of depth versus height at the same time. height keeps on cropping up in different ways in these geometry problems, and it becomes confusing. And there's a lot of different ways that height can be involved. So my situation is I'm a landscaper, contractor, and I have a customer who wants this really weird garden bed. The garden bed is going to be shaped like this. This has to be dug out of that person's backyard, and then this whole space, this volume of this shape must be filled with soil and compost and such to be able to plant things into. Why would it be a garden bed and not some object that sticks up off of the ground? If it's an object that sticks up off the ground, this would be the ground. And that's easy to see, and it's easy to see that therefore this is a height, this is also a height. We see how the word height applies easily to this. But if it's a garden bed, then there's the ground. And I'm not really sure where to put it here or here, but this is a hole in the ground. And then you think of depth for a hole. The depth would be 5 meters. But the depth and the height are the same thing. The depth of the hole in the ground is the same as the height of the object that's sticking up above the ground. So I did that on purpose with my situation to get the student to exercise those brain muscles where you realize that even though this is a depth, it's the same thing as the height. You're still going to use that h in the area formula. You don't change it to a d for depth. You don't have to. So that's one extra little thing that it could be in an exam question in that big paragraph that challenges the student a little more. Unfortunately, that sort of thing can make a student so intimidated that they can be tempted even to leave a question blank. A question that the student could have done. Okay, what else is there to talk about here? Let's talk about the amount of marks. Let's say this was worth 27 marks as a big exam question. What are the different levels of marks I could give for the different performances that students can give? We'll start with the bottom. A student who is intimidated by this situation and leaves it blank gets a 0. A student who scribbles down something just because they don't want to leave the page blank also gets a 0. And I have seen students who would draw something, even do 3 drawings without having done any of the calculations, without applying a scale. Their drawings are messy, they're not even using a ruler. It's very unlikely that I can give even 1 out of 27 marks to a student who did a sloppy drawing like that. Basically, an answer like that is a way a student is saying, I really don't care. I'm not prepared for this exam, and I'm okay with failing. Because if it's a 27-mark question and you get a 0 on it, well, probably you're going to fail the exam. Let's go up a level to a student who does a little better than that, though. Students can see a situation like this, and because they're intimidated, they can decide to pretend that this missing measurement isn't involved. They never make any attempt to find the missing measurement, but they manage to do the front view correctly in a scale diagram showing their scale, but the side and top views will be incorrect because they didn't know that it was 3 meters, so how could they draw these correctly? The 3 meters is never used in this drawing, so it doesn't cost any marks. It'll cost a lot of marks here. And even if a student guessed, they looked at the diagram and they thought, that looks like a 3, they're still not getting very many marks. Their diagrams would be more correct, but since they're based on a guess and not based on proven calculations, the mark is still very low. So students who pretend that the missing measure is not there or who guess at it might get 4 out of 27 or 6 out of 27. It's unlikely anyone doing that would ever manage to get even 10 out of 27. And we're still talking about probably failing the exam. Because let's face it, when you look at what I did and the difficulty of it and the calculations I had to do, this question is quite a gift. 27 marks for doing something this easy is quite a gift. Chances are that among the big questions on the exam, this is maybe the easiest one. So if you're going to throw away a lot of marks on the easiest question, you're in trouble. Now, what's the next level? The student realizes that they need this missing measure and they try to find it. But there are mistakes. The mark goes up a lot because the student's trying to find it when I'm correcting, my answer key is telling me to give marks to the student for trying to find it, also giving a few marks to the student for correctly finding it. Trying to find it is worth a lot. Correctly finding it is a little bit extra. So a student who tries to find x uses logical, mathy things that make sense to try to find x, but because of mistakes, incorrectly finds x, that student might get an 18 out of 27, maybe even a 20 out of 27. And at this point, we're talking about students who are very likely to pass the exam, because if that's the sort of effort that they make on a big question, and they do that on all the questions, getting that 60 and passing is within their reach. And then, of course, you have the student who did everything correctly. Well, that student gets 27 out of 27. I guess that was obvious. What if you do all the math parts correctly, all the calculations, but you don't understand how to do this type of drawing? That can really hurt you. I'd say we're talking about 10 out of 27 for having all of these calculations done correctly and none of the drawings are any good. But that doesn't happen as often. More often, I find that students are good at the drawings part before they become really good at all of these calculations, mainly because of the visualization that's required. I think maybe the most difficult thing about this question is, in order to do this step properly, we have to, in our minds, take this trapezoidal prism and sort of tilt it over so that the trapezoid becomes the base, because that's the way in which the formula works. And that little mental gymnastics that's required to realize that when I do that, my x now is a height. That's tricky, let's face it. Overall, what you want, if you're in the Math 3053 course, from a question like this, is you want to be able to use all the information that was given to notice and deal with things that the question wants you to do. And you have to know the different drawing types that are taught in the course. There are about 5 or 6 different types of drawing that are taught in this course. This is only one of them, this front, top, side view type of drawing. So the students should know it, and they should know the name for it. I haven't been talking about the lingo very much at all in this video. I'm not talking about it at all. I'm not going to say what type of drawing this is. If you're ready for this exam, you already know. Because the question could be written differently so that it uses the real term for this type of drawing and finds ways to not make this whole front, top, side thing quite so obvious. It's actually testing the student also on their knowledge of the vocabulary that came with the course. If you're ready for this exam, you're ready for any of the different types of drawings that are taught in the book, and you know all of the words, all of the terminology that go with each drawing so that you don't mix them up and do the wrong type of drawing than the one that was asked for. That, I guess, will be today's Daily Dose of Math. Please subscribe, share, and hit that thumbs up button.